Okay, starts recording. So today we have finished lecture 3 last time. So today we'll go to lecture 4 and talk about very important property of the probability law. In fact, last time we talked about several fundamental properties of the probability law. Basically, we have that union bound and the inclusion-exclusion formula. Okay. And today we'll talk about the continuity of the probability law. Okay. So the probability law as a function on events, we will show that it is continuous in some sense. Okay. So we can first recall the continuity of functions. Okay. Let's say we have function f that maps a real number to another real number. Okay. So we say the function f is continuous at a if limit fx when x goes to a exists and equals to fa. Right. So you consider a sequence of x that converge into a and looking at the corresponding function values. Now, if this sequence of function values has a limit and the limit exactly matches fa, then we say the function is continuous. Using a graph, we can, if you draw any continuous line as the graph of the function, and then this function is continuous. Because no matter how you approach, suppose this is A, no matter how you approach this point A on the x-axis, this fx is because the fx, this line is continuous. So we always have this equality. But an example of so this is a continuous example. A non-continuous example would be, for example, we have a jump. At this point A, and this is fx. So it's this fx is separated into two different segments, and here is a vertical jump. So fa equals to this solid point, but beyond that, the value of the function value has an instant jump. So in this case, this function is not continuous because if we approach this point from the right-hand side, okay, let's say x converge to, we can pick a sequence of x converging to a from the right-hand side. You can see that the corresponding function value actually converge to this point, but which is not equal to the function, the underlying function, the real function value of f at a. So this is an example of this continuous function. And we will see that for the probability law, recall that we have defined 3 different axioms for this probability law. And based on those axioms, we can show that this probability law is continuous in some sense. But because the probability law is defined on the events, we need to first talk about the monotonicity of the events. So to talk about the continuity of the probability law, we have to look at monotone events. The monotone events is a sequence of events that belongs to the sigma algebra that we just talked about in the probability space. So we have a sequence of events from that sigma algebra. And we say that this sequence of events are monotone if, so we have two different cases. The first case is called monotonically increasing. Let me actually, so we call the sequence of events monotonically increasing. Intuitively, that means the events, because all the events are subsets, are sets of the outcome space. So when we say the set is increasing, we mean the set gets bigger and bigger. So basically, we can say that the next event is the next event contains the previous event. Okay. For all k bigger than 1. Okay. So if you draw a graph, so this could be E1, and this is E2, and this is E3, okay, and go on. Right, so this is pretty much similar to when we talk about monotonically increasing real numbers, right? The values of numbers gets bigger and bigger. Here, we are talking about events, and events are essentially sets. So when we say this sequence of sets is monotonically increasing, we mean that they are getting bigger and bigger. And for this sequence of events, we will define the limit in this way. And this is just a notation. We define for this monotonically increasing sequence of events, we define the limit as the union of all the sequence of events. Okay. Intuitively, you can see that if the events is getting bigger and bigger, then the limit is essentially defined by the kind of the last event. So taking the union is equivalent to considering the last event, like the E infinity, because that E infinity includes everything, includes all the previous events. But here we still write this, we still take the union of all the events in order to clearly specify the sequence of events. So from this notation, we can see that this sequence of events evolves from E1, E2 up to EK. Okay. So we define the limit as the union of all the events for the monotonically increasing events. And similarly, we have monotonically decreasing. And you can imagine that in this case, E1 is the biggest. And then E2, E3, they keep. So the size of these events, they keep decreasing. So every subsequent event is contained in the previous event. So in this case, EK plus 1 is a subset of EK. Okay. Now, if we define, if the sequence of events is increasing and we define the limit as the union, because in the end, the limit is defined by the last event. Now, in the decreasing case, how do we define the limit? How do we properly define this limit? You can compare this increasing and decreasing case. Yeah. Yes, it would be the intersection, because eventually the limit is determined by, because the events is getting smaller and smaller, so the limit is determined by the last event, which is the smallest one inside all these events. So this can be obtained by taking intersection of all the events on this sequence. Okay. So here, I should know that these two are just notations, right? The real definition is here. It's the union of all the sets and the intersection of all the sets. Because these two are well defined. We know the union, we know how to take intersection of sets. So we can only define the limit of sets for monotone sequence of events. Okay. For other events, we can their limit is not well defined. So these are the only cases where we can define the limit. And in fact, so this concept of monotone events is very important in analyzing many probability problems. And let's consider a very practical example. It's called population extinction. So in this example, we consider a species that keeps reproducing over the different generations. And let's denote xk as the population of this species. At the end of case generation. So you can, for example, you can understand each generation as 1 year, for example. We're looking at the population of this species at the end of every year. And during each generation, the population may either increase or decrease depending on the distribution of the age of this among these species. Okay, so xk is corresponds to the population at the end of the case generation. And then we define the event ek as xk equals to 0, which means that, so this event means that at the end of the case generation, this species extincts, right? It has no population. So this is the event of extinction at the end of the case generation. And intuitively, we can also say that this event is equivalent to this is equivalent to this one. Because if at the end of case generation, this species extincts, then after that, right, xm for all m greater than or equal to k, xm are all 0 because the species dies out. So these two events are the same according to the for this specific problem. And we want to look at, so the question is, for this event EK, is it increasing or decreasing? Right. So EK means that, well, in the previous K-1 generations, the species may have some population, and somehow at the end of the case generation, it extincts. So that is the event of EK. So to consider this, to answer this question, we basically need to compare, based on the definition of monotonically increasing or decreasing. We just need to look at the adjacent events, see if the subsequent event contains the previous one, then it is called increasing. Otherwise, it is called decreasing, right? So follow definition. But how do we, for this example, how do we describe this event EK? So, okay, so basically we need to compare EK with EK plus 1. Right, and from this equation, we know that EK means that, so we have x1, x2, x3, up to xk minus 1. And starting from k, we have the species dies out. So starting from k, xk equals to 0 after that. So this is EK. And for the previous K-1 generations, we don't have any requirement. So except that they must be all positive. Because the EK means the species extincts at the end of case generation. So in the previous generations, the population must be positive, but we don't really know the specific population. So all these possible combinations, can be a proper event EK. So we can actually include this condition inside this set. Okay. For all the possible x1 up to xk minus 1, they must be positive. After that, they must be all 0. And similarly for EK plus 1, we just need to change k to k plus 1. So we have x1, x2, up to xk. Up to this generation, the species has positive population, and after that, it dies out. So which one is bigger? Which one is smaller for these two events? EK requires that after k minus 1 is all 0. EK plus 1 requires that the species extincts after xk. Which one is more stringent than the other one? Which one is more flexible based on these conditions? K plus one is more flexible. Right. You can simply set xk equals, I think we can include 0 here. We can simply set xk to be 0 so that ek plus 1 simply becomes ek. So this one is more flexible and it includes ek. Right? So ek is smaller because it requires xk to be exactly 0. But ek plus 1 does not have any requirement on xk. So ek plus 1 is a bigger one. It contains ek. So the subsequent event is bigger, means the event is increasing. So ek is increasing. So this is a sequence of monotonically increasing events for this example. And we will see more examples later. So for many problems, decomposing the event into a sequence of either monotonically decreasing or monotonically increasing events will provide much convenience in many cases. And then we can talk about this important proposition, which says that if ek, if we have a sequence of events is monotone, okay, if we have a sequence of monotone events, meaning that it could be either increasing or decreasing, okay, as long as it is monotone. For monotone events, we have this continuity rule. So the limit so the probability of the limit of this sequence of events equals to the limit of the probability of each event. Now, to be more specific, right, we can consider two different cases separately. So if ek is increasing, monotonically increasing, then this essentially, for monotonically increasing sequence of events, the limit is defined as union of all the events, right? So this essentially means that the probability of this event union event, equals to the limit of the probability of the individual events. Okay. So now these two sides, they mean different things, right? On the left-hand side, we are looking at, because, okay, think about this. Each ek is from that sigma algebra, okay? And from the sigma algebra structure, we know that the union of all these events, this as a big event, also belongs to sigma algebra. So that we can talk about the probability of this union event. Okay, so this is justified. And on the right-hand side, each ek is from the sigma algebra. So according to the probability law, we can talk about the probability of each event, which is basically a number between 0 and 1. And then we can consider the limit of this sequence of numbers. between 0 and 1. Okay. So both sides, they mean different things. But if the event is monotonically increasing, and these two, they match each other. Okay, and also similarly for decreasing case, the limit is defined by the intersection of all the events. And again, by the sigma algebra structure, the intersection of arbitrary number events is also an event belongs to the sigma algebra. So we can also look at the probability of this intersection event. And this proposition says that this probability is essentially the limit of the probability of each event. Okay. So the proof of this proposition is one of the homework. Okay, so I will leave it to you, but here I can provide you a hint. It is not, I think the hint is in the homework too, I remember. Okay, so you need to, the hint, I think I give a more specific hint. So the hint here, the hint here is to construct, okay, you have two cases, you need to prove two cases separately. So you look at the first case, you have a sequence of increasing events, right? You draw a picture, you have sequence of increasing events. And then we need to look at the probability of the union event. So the key idea is to, and you can see all these events, they are not mutually exclusive. And we have talked about this whenever we need to show something, prove something regarding the probability law, always think about transferring these events into a sequence of mutually exclusive events. So here we have sequence, we're looking at the union of this sequence of events. Okay, union is that consider everything contained in these events. Now, you can try to construct a a sequence of mutually exclusive events whose union equals to the union of EK. And the construction, I can give you a hint. Okay, you can construct a sequence of FK events that are mutually exclusive. So you basically start from F1. You let F1 equals to E1. And when you do F2, well, in the event E case, we have E1 and then we go to E2, but E2 contains E1. So why not just excluding E1 by considering in the second phase? So in F2, we just consider E2 subtracting E1. Right. In this case, the union of these two still gives the event E2, but they are now mutually exclusive. Okay, and you keep going, F3 is, no, E3 subtracting E2. But you can, it is more convenient to write it as union of E1. 1 to 2. Okay. But this union is essentially E2 because E2 contains E1. but this helps us to establish the proof later. And you keep going on, Fk is basically Ek, and subtracting all the previous. Need to use a different subscript, I. Okay, you do it like that. So on one hand, the union of Fk equals the union of Ek. So you can replace this union by the union of Fk. And now the Fk are mutually exclusive. So you can apply the one of the axioms of probability law to decompose this part. Okay. So you will have, because Fk's are mutually exclusive, so the union Ek equals to union Fk. This is by construction. And then Fk are mutually exclusive. So the probability of this union equals to the summation of this one. Okay. By the probability law. By the axiom of the probability law. And then think about how can you proceed and claim that this is equal to the limit of Ek. Think about that. Okay. Oh no, think of this is yeah. Think about how this is equal to the limit of the probability of Ek. Okay. Okay, you need to fill this gap. Okay, and this is for the first case, increasing case. Okay, for the decreasing case, you can, well, here we are talking about unions, but in the decreasing case, we talk about intersections. So you can think about how to construct another sequence of mutually exclusive events, whose intersection equals to the intersection of the events, original events. Okay. So this is the continuity of the probability law. As long as we are considering a sequence of monotone events, the probability law is continuous. It's continuous. Okay. So any questions? Okay, so let's consider a very challenging example. Well, at the first glance, it may seem very complicated, but once we leverage this monotone event structure, it can substantially simplify the problem. And this is how we solve many complicated probability problems in practice. So we generate a sequence of numbers, sequence of integers following the following rules. So xk, all these numbers are distinct. Right, so none of them is equal to each other. They are totally different numbers. But how do we generate them? Well, this is how we generate. Xk is generated from this set. Right? It's generated from this set of integers, and we picked it uniformly at random. from 1, 2, 3, 4, 5 up to 10 times k. We pick xk from this set of integers uniformly at random. But we need to satisfy the first rule, right? It must be xk must be different from everyone else. So so we need to add one more. We need to exclude excluding all the previous generated numbers. Okay, so basically this is how you generate. For xk, you first remove all the previously generated numbers from this set, okay? And for the rest of the numbers, you pick one uniformly at random, and that is xk, right? So you first generate x1. For x2, you exclude x1 first, and then generate x2 uniformly at random, and so on. And so this is how we generate all this sequence of numbers, of integers. Okay, the question is, what is the probability of this event? The event E is defined as the number 1 never appears in the sequence. So it's basically all the xk's are not equal to 1, are not equal to 1. What is the probability of this event? Well, if we don't have this first rule, if we don't have this first rule, if we don't exclude all the previous generated numbers, so let's consider a simple experiment where every time we simply pick xk uniformly at random, okay, from this set. Then this probability is very simple, because every time we just need to make sure every xk does not equal to 1. And the probability of that happens is equals to 10k minus 1 over 10k. Okay, because all the rest of the numbers can be a proper xk. And then we just multiply all these probabilities together, because every xk is independently generated. But now since it gets more complicated, because we need to make sure they are distinct. And this is achieved by every time for xk, we need to exclude all the previous numbers and then sample xk for the rest of the numbers, from the rest of the numbers. So this makes that xk is dependent on the previously generated numbers. So they are no longer independent anymore. Okay. So this is the challenging part of this problem. Right. So do you have any ideas how to decompose this event? Right. This event E means that 1 never appears in all these generated numbers. So what is a proper way to decompose this event? So what is equivalent to this event? What other events is equivalent to this event? Well, the first idea came into my mind is like, if you look at this event, it never appears meaning that it simply means that every number should not equal to 1. Right? But as we said, we cannot separate these events because each xk depends on the realizations of all the previous numbers. Okay, depending on how we generate the previous numbers, the ways we generate xk would be different. So this makes it very difficult to directly decompose all these xk's separately. So we need to think of another way where we can kind of avoid this dependence. So this is how we decompose the event. We can define a smaller event ek, which means that this number 1 does not appear in the first k numbers. Okay, so event ek means that 1 does not appear in x1, x2 up to xk. So here, instead of considering each xi individually, every event ek, we consider a bunch of xk's up to the case iteration. Okay, we consider this set of xk's. And comparing ek with the desired event, the target event that we are looking at, E, we know that E is like the limit of ek as k goes to infinity. Because this event E simply means that this number 1 never appears. But ek says 1 never appears in the first k numbers. So if we push this k to infinity, then this ek simply becomes E. But the question is, can we properly define this limit? And if you look at this ek, you realize that it is a monotone event. So the question is this a monotonically increasing event or decreasing event? If you compare ek with ek plus 1, which one is smaller? Which one is bigger? I think ek is bigger because ek plus 1 requires 1 to not appear in xk plus 1. But in ek, we do not have that requirement. Right, so this ek is bigger. Ek is bigger. So this is a monotonically decreasing event. Right. So we can write down the definition of ek plus 1, where 1 does not appear in the first k plus 1 numbers. So which means that x in the ek plus 1, xk plus 1, this number should not equal to 1. But in this ek, we do not have any requirement on xk plus 1, right? So ek is more flexible, right? So this is a smaller event. It is more yeah, this is a smaller event. Well, ek is more flexible and it contains ek plus 1. So in the ek, in this event, right, it is possible that xk plus 1 equals to 1. We don't have any requirements on that.
What about EK was defined in that one that's K numbers?
Yeah, in the first k numbers. Right, so here we only have k conditions, k requirements. Every x1 should not equal to 1 up to xk should not equal to 1. But in ek plus 1, we have an additional requirement that xk plus 1 should not equal to 1. So ek plus 1 has more requirements, has more restrictions. So that's why it's a smaller event, right? So in this sense, this ek is monotonically decreasing, and because it is monotonically decreasing, we know that we have a proper definition of limit, so we can just define this this limit is essentially the intersection of ek. So in this way, we decompose the big event E into an intersection of smaller events. And by the continuity of probability, right? If we want to look at probability of E, which we know that it is equivalent to the probability of this intersection event. Okay, this is by our construction, and by the continuity of probability law, we know that this is equal to the limit of probability of ek. Let k goes to infinity. Okay. So we just need to calculate. The probability of ek for each k, and then push that to the limit. Well, probability of ek corresponds to the probability that 1 does not appear in the first k numbers. Okay, let's look at this one. Probability of ek, which means the first k numbers should not equals to 1. Okay, now go back to the number generation process. Can we calculate the probability of this ek? Well, okay, so this is how we generate each xk. Now, what is the probability? Is this easy to compute? Question is, can this be computed easily? We can simulate this process. Okay. So x1 is picked from 1 to 10 uniformly at random. Right? Because if you go back to the here, xk is picked from 1 to up to 10 times k. So when k equals to 1, it's from 1 to 10. Okay. So this is how we generate x1. But to make sure this happens, to make sure EK happens, x1 should not equal to 1, right? So what is the probability of x1 not equal to 1 when generating x1? So we pick x1 uniformly at random from these 10 numbers, right? And what is the probability that x1 is not equal to 1?
Wasn't it 10K and it was 10K minus
So we
1
pick
over
every
10K?
number equally likely, and right. So there are in total nine cases that satisfy this condition, right? Over the in total 10 sample size. So it's 9 over 10, because the probability that you pick 1 is 1 over 10, right? So x1 not equal to 1 has probability 9 over 10. Right? So this satisfies x1, the condition on x1. And then to generate x2, we know that x2 is generated from one up to 20, and excluding x1. So here's the case. We know that x1 is not equal to 1. So this x1 must be something between 2 and 10. And then we are when we generate x2, we are excluding this x1 from this set of 20 numbers. Now, what is the probability that x2 is not equal to 1? Well, in total, we have 19 candidates to pick, because here we have 20 and we are excluding the previous x1. So in total, we have 19 candidates, right? From that 19 candidates, we pick one of them. So what is the probability that we do not pick this one? It should be 18, right? So that one is the. So x1 may be, so we are excluding x1, so there will be totally 19 candidates. And among these 19 numbers, what is the probability that we do not pick one? Well, it is the probability when we pick the other 18 numbers, right? So it's 18 over 19, right? Because we pick every number equally likely. So it's 18 over 19.
I have a quick question.
Okay, hold on, let me. Yep, can you hear me?
Yeah,
Okay, yeah, so what is the question?
I thought that each x1 was chosen just between 1 to 10K each time, not from 1 to 20 and then 1 to 30. I thought it was between 1 to 10K.
Yes, exactly. So to be more specific, right? So so let's write. Okay, let's write down everything from this set up to 10 and 11 up to 20. So this is the original set for x2, but now we are excluding x1. So x1 is, we know from the first case, we know x1 is not equal to 1, so it must be generated between 2 and 10. So x1 is somewhere around here. So we are excluding x1.
Oh, I think
But-
I misunderstood the rule number 2 at the very beginning of how the set was generated. I thought it was
Okay.
1 to 10,000 instead of the K being multiplied by the 10.
Oh yeah, that K is not 10,000, it's not 1,000. Yeah, it means the index K. Yeah. So here 20 is 10 times 2, the index 2, right? This is 10 times 2.
Yeah, I think I understand now. Thank you.
Okay. Questions? Oh, because according to the data generating process, we first we first need to exclude all the previous numbers and then sample xk from the rest of the numbers. So that's why when we generate x2, we first exclude x1 and then pick the x2 from the rest of the numbers. Yeah. So x1 is somewhere around here, and we are removing x1 from this set. So in total, we have 19 candidates left. Among the 19 candidates, you can see that we still have one, because we know that x1 is not equal to 1. We still have this candidate 1. So we are looking at the probability that x2 is not equal to 1. So that is, well, among these 19 candidates, we can pick the rest of the 18 candidates. Right? So it's 18 over 19. And for xk, it's the same thing. So we have in total this many number of candidates, but we need to exclude x1 up to xk minus 1. Okay. So there are in total 10k minus k minus 1. This many number of candidates. Like here we have 10k, here we have k minus 1. So in total, we have this many number of candidates. And among them, in order to make sure that xk not equal to 1, it's just this number minus 1. And this, if you simplify that, that gives 9k over 9k plus 1. So this can be written as a product of fraction numbers, right? So when n equals to 1, we have 9 over 10. When n equals to 2, we have 18 over 19, right? So they match this formula. So this is essentially the probability of EK, okay, which is written as a product form. And now we have this, so this result is obtained. So we just need to take the limit, okay? So P probability of E is equal to the limit of this probability of EK. So we just need to consider this limit. So what is the limit of this probability? So that is the final question. Well, intuitively, you can say, if you look at this product, every time we are multiplying a bunch of fraction numbers that are strictly less than 1, okay? Because 9n over 9n plus 1 is less than 1. So when you multiply something less than 1, the number gets smaller. Okay, so you have an intuition. Well, this number is decreasing, but you don't really know if it decreases to 0 or some number that is bigger than 0. So here we can try to estimate this number. So this is how we do that. So this number, this fraction number equals to this one. And here, I use a very famous inequality Well, this inequality says 1 minus x less than equal to e to the power of negative x. Okay, this holds for any real number x. So here I replace x by 1 over 9n plus 1, right? So apply this inequality, we get this one. Well, the reason we do this is that, and then we have exponential, and the product of exponential is easier to handle. And then this product can be absorbed into the exponential as a summation. Okay. And and then when we consider the limit, when we push the k to infinity, this side, when we push k to infinity, this part, this summation diverges to infinity. Okay. So this is a summation over a series, like in the order of 1 over n. So when we sum up this series by the integration rule, this is approximately logarithm of k, and logarithm of k diverges to infinity. Okay. So in mathematics, we have result to say that this series diverges to infinity, summation series diverges. And this is essentially 0. So in the limit, this is 0. Okay. But this is less than or equal to, right? This is inequality. So we are the probability of EK, we are upper bounding the probability of EK. Now, even this upper bound, this bigger number goes to 0. So we claim that, so we can conclude that this limit is 0. Okay. Because we are upper bounding this probability of EK by a bigger number. And then we show this bigger number, this upper bound goes to 0 in the limit, right? So the upper bound goes to 0, and on the other hand, the probability should be greater than or equal to 0. So when you so the lower bound and upper bound, they coincide, meaning that the only thing we can happen in the limit is 0. Okay, so this is the final result. So the probability of this event, is 0. So that means the probability that number 1 never appears is 0. Or to put it in another way, the number 1 will appear in one of the numbers xk almost surely, right? The complementary event must happen almost surely. Right. So from this example, we can see that, to summarize, the main technique that we are using here is that, first of all, we realize the numbers are dependent on each other. And in particular, the case number depends on the previous number, all the previous numbers. So this is a very special dependency structure. So that's why when we decompose the event E into this EK, we actually include all the previous numbers, because we know xk depends on all the previous numbers. So why not just include all the dependency in this event? This is a way to decompose the event. And when we include all the dependencies in the up to k in this event ek, we can see that this event EK is actually not that hard to calculate. The probability is not that hard to calculate. We just need to go over the generation process, and following this process, we can figure out the probability one by one, and then multiply them together. And in the end, we just need to calculate the limit. Okay, so this is about monotone events and continuity of the probability law. Okay. We'll see some examples in the homework problems. And then we talk about, we have 13 minutes left. We can briefly introduce the conditional probability. Well, we consider these three elements of the probability theory as a set of all outcomes. And then from over this set of all the outcomes, we can define the events as subsets. We collect some events to form a proper sigma algebra. And on that sigma algebra, we can define this probability law. Okay, these are three elements. So let E be an event from this sigma algebra such that it has positive probability. Then the conditional probability of another event A given E, given this event E, is defined as, so we usually write probability of A given E, right? This is how we, even in the classic probability theory, we have this definition. The probability of one event given another event. But now we have all this, now in the modern probability theory, we describe everything in the language of set theory. Okay, so here the definition of this is just notation. Again, this is a notation. The specific definition of this conditional probability is given by the ratio between the probability of the intersection event over the probability of this conditional event. Now, let's think about this. On the left-hand side, it's just a notation, right? It means probability of A given E. But on the right-hand side is the specific definition. And you will see, and you can see that everything on the right-hand side is well-defined and justifiable from the modern probability theory. First of all, because E is from the sigma algebra, so we can talk about its probability, P of E. The probability law will assign a number, right, to every event from the sigma algebra. And here we require this probability of E is greater than 0, so we don't have that issue. When we are not dividing by 0, we don't have this diverging issue. So this denominator is well defined. The numerator is also very well defined because A and E, these two events are both from the sigma algebra. So their intersection, right, by the structure of sigma algebra, their intersection is a set that also belongs to that sigma algebra. Okay, so this set is also belongs to F. That's why we can talk about the probability. So the probability law will assign a probability mass to this intersection event. Okay, so this is also well defined in the modern probability theory framework. Right. So whenever we talk about conditional probability, it really means the right-hand side. Okay, the right-hand side. So if you can draw a picture to illustrate, suppose this is A and this is E and this is their intersection, right? So the conditional probability is essentially the ratio between, like the numerator is the probability of this intersection area. So it's like this. Intuitively, if everything is uniformly distributed, right? So this conditional probability is kind of measuring the ratio of this shaded area over the event, the area of event E. Okay, so it's this conditional probability. Okay, so this is the definition. And there are some very simple implications. So from this result, we can say that the probability of this joint event, you can move this denominator to the left-hand side, equals to this one. Right? And this is how we usually decompose the joint event. You can decompose the probability of the joint event into the product of the probability of one of the events multiplied by the conditional probability. Now, if on the other hand, if the probability of A is positive, then we can decompose it in another way. Okay. You can decompose, so both of them equal to the probability of the joint event. You can either decompose it in terms of probability of E and multiply it by this conditional probability. It's A given E, okay? Or you can decompose it in probability of A multiplied by the another conditional probability, which is probability of E given A. Okay, so the order is different. And the last one, here we are talking about the joint event between two events. We can also look at the joint event over a finite number of events. Okay, so this is the joint event over n events. Okay. So the probability of this joint event we can start from any of them. For example, start from the first one and then multiply by the second one given the first one. And then the third one given the first two. Okay, and so on, multiplied by the last one, given the joint event of the first n-1 events. So we have 4 minutes to talk about this. The proof is very straightforward, but we can just follow. Okay, follow all the definition and axioms of probability and try to rigorously argue this one. So I can first view this as E1 intersection of okay, let me remove this. Right, because it's an intersection. So I can first take intersection for the rest of the events and then take intersection of the E1. So this can be viewed as the intersection of these two events. And then I can apply the definition of conditional probability to decompose it as this. Right, you just view this entire intersection as a single event. So just apply the conditional probability rule. And then we need to further look at this one. So again, you follow the same strategy. You can write this one as E2 intersect the rest of the events. Okay, now think about this. I can put it here. So it's probability of E2 intersect and this one given E1, right? So you can again apply the conditional probability. So it will be probability, but see, note that here everything will be conditional on E1. So when you do that, it's E2 given E1 multiplied by this event given E2 and the E1. Okay, so that's why you have the second term. Okay, here you have PE1. Here you have probability of E2 given E1. So you have the first two terms, and then for this term you do this. You continue decomposing this like that. You will have the third term and so on. So this is how you can prove this by induction actually. Okay, so I think I will stop here and you can start to work on the homework 2, which will be due next Monday. So that deadline is next Monday. And I will hold office hours in the afternoon in the classroom. Okay. Okay, thank you guys.
So we do these physically.